STTP, on artificial intelligence for IT infrastructure management and automation. The speaker of the session is Dr. Krishna Sivalingam. He is an institute chair professor in CSE department, IIT Madras, Chennai, India. He received his PhD in 1994. He was a faculty member in University of Maryland, Baltimore County, Washington State University, in Pullman, and University of North Carolina, Greensboro, all in USA. His research interests include computer networks and wireless networks. He is an IEEE Fellow, INAE Fellow, and ACM Distinguished Scientist. He has served as editor-in-chief of Springer, Photonic Network Communications Journal, and EAI Transactions on Future Internet, and is presently an editorial board member of IEEE Networking Letters. On behalf of the Management and Department of Information Technology, I especially Dr. Krishna Sivalingam for accepting our invitation and to share his knowledge and thoughts on the topic. Over to you, sir.
Thank you, Madam, for the introduction. I'd like to thank KCG College for inviting me to give this talk. Good morning, everybody. I presume that, Madam, to understand the audience, that STTP is mainly for college faculty.
Yes, sir.
Okay, all right. All right, so I will try to give an overview of the topic that is presented. It's an approximate match to the overall theme of what this STTP is organized about, but let's see how it goes. So let me try to share my screen, if that will work. Okay, is the screen visible? Is the presentation on?
Yes, sir, it's visible, sir.
Okay, all right. Okay, let me hide this. So again, once again, good morning, everybody. So the presentation is titled AI and ML Techniques for Infrastructure Management, and in particular, focus on orchestration in 5G networks. A lot of buzzwords in here, and as you can imagine, this is right. It's a very in-depth topic. There are a lot of things to be covered, and it's nearly impossible to cover this in like a 1.5 hour lecture or so. So anyway, I'll just to give an overview, and the main thing I wanted to give was some pointers to problems in the space that others have been working on and what can be done in the space. Okay, all right, yeah. So first we'll start with the acknowledgements. So my lab at IIT Madras is called the DONG Lab, which is working on computer networking primarily. And the key group members who have been helping me with preparing this material for the past several months. We've been working on this for the past few months, almost a year now. Radha Krishna Kamath, MS Scholar, Saurav Chakravarti, and MS Scholar, Akhil and Sai Kiran, who are project associates in my group. Funding for this work has come from the DOT, the Department of Telecommunications, who funded our India 5G testbed, as well as VMware, who has been funding our research for the past 8 months or so on ML for 5G network slicing and resource optimization. Okay, let me just take a quick pause here. I'm trying to get the system sort of optimized. 1 second, please. Okay, sorry, I'm back. So the contents of this presentation, let me see my so in general, right, what is the computing infrastructure that we are talking about? Now, this is probably evident to many of you, especially if you have been teaching some cloud and relevant courses. Then I'll talk about briefly what are the challenges in terms of operational challenges and optimization, right, in terms of the system operation and management. So these are very high level, right, inputs into what we are looking at in terms of system definition and what we expect from the system. Then I'll move on a little bit into 5G because cloud computing is such a vast area and with so many applications. I thought I'll focus a little bit more on the 5G project. This is again funded by DOT, and talk about 5G and the cloud connection, right, as to where 5G networks and clouds come together to deliver the services for customers. And again, there is no feedback right for me. So if there is any question in between, you can stop me and raise the question, because otherwise I'm not sure if I am actually connected all the time. I can, except the red recording blinking light, I cannot see any other feedback. Okay, so please feel free to stop me and raise the questions so that I know that I have a live audience. Okay, and then so coming to 5G again, so what are the infrastructure management tasks in 5G cloud that we are looking at that can benefit from some of these things? Then I'll move to the second half of the talk on, right, once you've set the stage for 5G and cloud, what is ML for networking, and what are things that people have looked at in terms of right, ML techniques in computing infrastructure management. And then with that, of course, a little more detail in that last bullet, use cases. But then I'll finally conclude after I present some of the recent topics in terms of resource optimization, applications of ML and RL and DRL, etc. So I'll give a flavor of the kind of problems that people have been looking at over the past few years. Okay, so we'll first talk about the cloud computing infrastructure. Is everything okay? Are audience able to hear me? Can one of you unmute and give me the okay?
Yes, it's audible.
Okay, good, thank you. Okay, so we'll look at just to rate, I guess it's a rainy day, at least in Chennai. So we kind of wake up with some concept that we already know, right? So if you look at computing, right, computing has been always centralized, then it went to decentralization, right? Then it became centralized again. So the arrows might not mean much, but right. So we started basically centralized systems, and we came down to decentralized systems, and we keep going up and down. So this the original centralized system was, of course, mainframe systems. Then we went into right in the 80s with personal computers, which then followed with workstations like the Sun workstations, Solaris workstations, and then which moved on into Dell workstations and so on, where we started doing a lot of our computing. But then over the years, this model is again sort of evolved back to a centralized computing environment, which we call as the cloud today, or data centers, which is where right a lot of the computation takes place for many of the applications today, including content delivery networks, including all the stuff that we see on email, and of course now with the Zoom call that we are having, right? It's again a centralized system where things go to a central server and are then routed, right? It's more like a multicast environment. So if you look at mainframe versus cloud, right? In the mainframe system, the hardware, operating system, software all were closely bound together, right? I mean, IBM wrote everything, right? They wrote the compiler, they wrote the OS, they built the hardware, so it's a very tightly coupled system. And today we can say the Apple, right? Apple Mac, Apple Book, MacBooks are in the similar class. And right, there was a very specific storage to processor binding, so it's all very tightly coupled in the right olden days. Then we moved to a decentralized system where the OS, of course, was still tightly bound to the hardware, but the application software, right, that people could use, compilers that people could use, they are no longer right tied to the specific operating system. You can write, of course, you can port applications across operating systems. Compilers can be used, different compilers can be used on the same operating system. And also networking protocols, we used to have, right, IBM specific architectures in the 70s and 60s, but when it came to 80s and the, right, the TCP IP standards started coming into play with OSI models and so on. Okay, so this is sort of the other end of the spectrum where we completely moved from decentralized to a very decentralized environment. And if you recall, in the 90s, people were talking about network computing, grid computing, cluster computing, right? All those terms were there, which was again sort of this decentralized model of computation. Then we moved on into right sort of the 2000s was when Amazon started right looking at cloud computing as the Amazon Web Services, one of the earlier users. Of course, there are other services too, but AWS was one of the first to sort of come on the market. And here, right, the things are different in terms of the hardware hardware operating system binding is loose. I can run any OS and any hardware. And of course, the specific OS software binding is a little bit there. And network environment is a little bit more specific because compared to the personal computer world, where TCP/IP has to be used across sort of the globe for the sake of compatibility, inside a data center, I can use pretty much any network protocol that I want, right? Only N hosts have to worry about maintaining the same network protocol, but inside the data center, I can use something that is more optimized for this particular environment. Okay, so this is sort of right, the gentle introduction to what cloud is, which, like I said, many of you probably are already aware of. So then, if you want to define the term cloud computing, right? Cloud computing, there are many definitions, but the simplest definition from this thing grid that I picked out is from 2011 or so, right? Refers to the highly scalable computing resources provided as a service by via the internet on a pay-as-you-go basis. That still applies today. For example, if you want to even open a small startup company and all you want is 5 virtual servers, you simply sign up with Azure or AWS or Google Cloud or even TCS data centers in India that can get you the resources you want on on an hourly basis or on a use basis and so on, right? So this is essentially elastic computing world where resources are not purchased ahead of time. You simply use them when you need them, right? So that is the general model of what cloud computing is all about. And a lot of drivers that made cloud computing possible today, right? One is, of course, right, ad hoc service hosting. So I can host any service that I want on any computerized system. And the other thing was grid computing, which I said was the popular thing in 80s that led to right, the decentralization. But then it helped again in the context of centralization when basically what happened in the olden grid computing days was I have a network of computers, and any computer that is on the network that is not fully utilized, right, was released for use by other computers. For example, people used to do this extraterrestrial search, right, for intelligence, and search for extraterrestrial intelligence was done using these spare resources. But then if you look at the history of how Amazon started using or creating this data center environment is when right, the Amazon CEO found that there are a lot of data centers and computing resources that Amazon had built for its own right use for internal purposes, and a lot of those machines were idle much of the time, and therefore they decided to make that into something that is meaningful, right? Basically lease out those services to somebody who wants computing power. That's sort of how, right? And instead of voluntary sharing, the sharing became sort of on a commercial basis where anybody who wanted hardware resources and storage resources could go to the centralized cloud environment and get that. And the other technology that was key was virtualization. So many of you would have heard of VMware, right? Virtualization. It started in the late 1990s. I've used one of the early versions of VMware, where it was simply a way of getting around the dual boot operating system that we used to have in those days, where I can run Windows inside Linux or vice versa. And that was considered a big boon in those days because I otherwise had to always boot from Windows to Linux, back to Windows, and so on. Right. So virtualization technologies came about, which then helped this notion of right freeing the underlying hardware from the software that runs on top of that, from the OS that runs on top of that. Okay, so there are some issues, of course, with virtualization. There is emulation overhead. So, but now there are ways of running hypervisors on bare metal without running an intermediate guest operating system or host operating system. I'm sorry, right? So these are some of the technology drivers that led to sort of the more widespread adoption of cloud computing as we see today. Okay. And so essentially what we see here is, right, sort of just to put this in a perspective, is at the lower part of the pyramid is the cloud computing infrastructure. And then you have the cloud operating systems and interfaces that sit on top of that. And then finally, cloud applications to which the users are interconnected. This is sort of the overall picture that we see now. There are different types of cloud services, infrastructure, right, as a service, a platform as a service, and software as a service, and so on, which I will not go through because many of you are probably aware. And we use this on a daily basis without even being aware of that, right? But mostly we talk about infrastructure as a service as one of the main systems, like, for example, Amazon's, right, cloud offering, whether it's still called EC2, I'm not sure. But Amazon's overall cloud offering is there. And there are other types of infrastructure that provides different services, which I will not elaborate upon. Okay, and then there is a notion of public cloud and a private cloud, hybrid cloud, which most of you are probably have heard these terms, but there's nothing very different. The names imply that public cloud is something that you take from, right, that's available publicly in the public domain, whereas private cloud is something that an enterprise operates by itself without using any external resources or services, right? And hybrid is where you have a mix of both internal and external service providers. So this is again just a filler diagram that shows, right, for example, Amazon Web Services has a lot of components that make up the overall infrastructure. I'm not going to elaborate on each of this. This is just to show that the system is fairly sophisticated today in terms of various components, right? We have storage component and the UI component, and then there is the discovery component, data component, and so on. And all of these put together, right, is what the users get to use for, of course, pay for payment as they go along. Okay. So in case you're wondering what a data center looks like, and if you have never seen one, I have not seen one insights either. Okay, this is a picture from Google Data Center in Iowa. And this is just showing you the racks of servers. Of course, various colors are there. I do not know why some are blue and some are yellow, but that's what we have. And actually the systems when it looks like this, right? We have a whole bunch of racks, and there are a lot of servers on the racks, and these servers are interconnected by these cables that you can see, right? There are optical cables and there are all sorts of cables going around. So this is essentially what the infrastructure that is there, right? That makes up a cloud center. And this is where we pretty much, right? If you're watching YouTube, it's coming from a center like this. If you're on Gmail, then this is where it comes from, and so forth. And many other applications, right? All the content delivery. If you go to CNN, the CDN is also hosted in one of these Akamai kind of data centers, which then actually supplies the data. And this is just for fun to show this is beneath the data center, right? The data center generates so much heat that they actually have these huge coolant systems at the ground floor level, and at the first floor floor above this is where all the computing systems are stored. But you need like a mini cooling plant, right, underneath every floor of the data center. And things got better where they could then take data centers and containerize them, as in this IBM container, or even you can put them on, right, trailers, tractor trailers, and then send them across the country, where you can set up, for example, if you're running a IPL match, then you would need something like this, which is locally going to, right, cater to all the data. And then if it's running a web service, right, like uh, an IPL match you're watching on Hotstar, then you have your own data center that can, right, transmit the data live from one of these data centers. Okay, so this is a gentle introduction to what virtualization and what cloud computing systems are about. Now, this is the infrastructure, right, that we talked about. So I'm sort of justifying the title infrastructure, the word in the title. So now, in terms of right, where do we need the machine learning techniques, right? So all this is well and good, but underneath the hood, what is needed, right? So one of the common tasks is provisioning. Okay, so this provisioning involves figuring out a lot of cloud configuration parameters. For example, I'm building a data center. Then I should decide how many racks do I have. You saw those sequence of racks out there. How many racks do I need? And how many servers per rack do I put? Okay, so that's usually physical space constraints. And then for each server, how many CPUs do I need? Is it 4, 8, or 16, right? How many slots are there on a server? And the number of cores per CPU, is it 8, 10, 16, 32, right? What are the number of cores that each CPU will require? And then main memory size, right? I'm going to put a terabyte of main memory on each server, and cache memory size. I mean, these are all, right, realistic sizes today, that these large memory sizes are needed, because I'm going to share the server across multiple virtual machines or multiple containers. And to do that effectively, main memory is one of the most crucial, right, shared resource. Then disk capacity per server, because I have to do a lot of computation, and I'll be dealing with large files, right? If I'm doing sort of map reduce kind of computing, so where do we store those data files, right? Local storage, and there is also network attached storage, which is again of the order of multiple petabytes, and or even at much in larger scale. Then what about the underlying data center network? How do we interconnect all these servers? What is the topology? What is it, a factory topology or some other topology? And what about provisioning the links in the data center, right? Do I do 100 gigabits per second? Is that sufficient? Or should I go to 400 gigabits per second, or even much higher, right, capacities in the data center? And what about redundancy? What happens if a network link fails? I have to make sure that the network is still connected, right? And redundancy applies to servers also. If a server goes down, it takes down all the virtual machines and containers on that server. So how do I restart that service quickly such that I can, go back to serving the customer again? And what are the underlying operating systems that I'll support, and what kind of virtualization platform will I use? So a lot of configuration decisions have to be made to just bring up a data center, right? To decide before I build a data center, I have to figure out all of this. Now the question is, what input do I have? Well, some of this you take from your past experience as a data center provider and figure out that I know I'm going to build a data center of this size and I hope that I can serve so many customers, right? And if things get bad in terms of provisioning of capacity, then you start using adding resources to the network, right, on a demand basis. So a lot of challenges, like I said, how to obtain the initial capacity requirements, right? It's mostly based on guesswork, experience, and some past data. And how do I decide the initial data center configuration, right? All these things have to be considered. These are all challenging problems. People have addressed these in various settings across the globe, right? In various research institutions, in various companies which are actually dealing with this, right? And most importantly, how do I scale the compute, storage, and network capacities of the center, right? Am I right? If the system response time goes very high, it probably means that there are too many servers, virtual servers running on the system. Then what should I do? How can I accommodate more customers and still be able to give them the same kind of quality of service, right? So the methodologies that people have been using are, right, simple naive techniques might sometimes work for these. Heuristic techniques, right? You can come up with all sorts of combinations of how to derive heuristics to serve these particular optimization criteria that we are looking for, or go in for more, sophisticated but more accurate optimization techniques. But as you know, these are usually done offline, and the complexity of the scale of the problem is so large that you cannot really solve them in a real time, right, using optimization techniques. Even not forget real time, sometimes it's not even possible to solve them even in days or hours, right, or in days or months time frames. So you'll have to go for some sort of suboptimal solutions also. And this is where, right, machine learning can play a role, which people are trying out now. It's not like, they have solved the problem and that ML is actually going to be the way to go. One can always look at a simple heuristic. Now the challenge is, can I do something with machine learning, right? Some of what kind of techniques we'll see later on, right? To in order to do some of these optimization problems, right? Like again, optimization, many of you are aware of, all these sort of genetic algorithms and right, various other techniques that you would see, and colony optimization and so on, right? Would those be sufficient along with heuristics, or will a sophisticated machine learning algorithm actually come in and change the game such that they're going to make a big difference? Okay, so right now I do not know if there is, I cannot know for sure if that's going to be a right definite winner, but right now ML is the flavor of the day, and therefore it makes sense to try out whether these techniques, which have been used in other domains primarily. So if you look at the use of ML, right, it has been used very well in natural language processing, in image processing, in vision, and right, and video processing, and so on. But when it comes to actually using this in the context of system optimization, okay, that is still, I think, an open area of research. So some of you are looking for research topics, then right, you could look at some of these also as we go along. Okay, so then that is the initial stage, setting up the system. Then next is the operation stage, right? So there are going to be a steady stream of requests that come in. People will request virtual machine or virtual data center configuration, and there are a lot of parameters that define a virtual data center, right? What kind of OS do I want, and do I want a virtual machine or a container, right, on my system for running my applications, and how many virtual CPUs, virtual cores, virtual main memory, right? All these things that I will require is what I would specify to the data center. Now, there's a resource allocation problem, right? How do I efficiently allocate resources such that I can not only satisfy the current demand, I can also satisfy the future demands, okay? And so that is the sort of some of the optimization problems that one has to deal with in terms of resource, right, allocation. So again, a lot of challenges that has to be addressed, right? Each of this can spawn multiple publications if you, right, look at it carefully. How to allocate initial resource requirements, right? How is the efficient way to allocate this? Which virtual machine, which virtual CPU goes on which physical server, and where do I place them, right? Remember, this can be across global data centers also, right? So is it okay if I get a couple of CPUs in Singapore, couple of CPUs in India? Will my system still perform in terms of my expectations as a user, end user? Okay, and so how to ensure that the user's requirements are always met, and how do you achieve load balancing at data center level? For example, you want, right, all the servers, if they're to be up, then they should be running at roughly the same load or utilization. If some servers are idle and some are running at very high utilization, then you have to do load balancing. Other challenges are how to minimize power consumption at the data center level, and how and when to migrate virtual machines containers, how and when to add system capacity, right? So there are a lot of challenges that come at the operational stage, right? In terms of maintenance, in terms of management and running the system, right? There are several challenges that one has to look at. So each of these, like I said, right, can spawn a sort of individual problems that one can define. And methodologies, again, we probably will see a combination of naive techniques or heuristic techniques or optimization techniques. And here again, right, can ML really do the job for us? Because remember, ML is a very time-consuming operation, and I'm talking about real-time, right, use of ML techniques for actually generating, for actually handling system operation, right? So will ML systems really be useful? Well, I do not know the answer to that, like I said before, but perhaps with more research and more understanding, one can find out areas or sort of niche right problems where ML can actually make a big difference. For example, you can use ML for prediction, right? If you want to do prediction of load, then ML techniques, which are the old statistical techniques, right, can be used with some current modification. So there are lots of these challenges. So in summary, right, what I presented so far is I've talked about the infrastructure, which is the cloud computing infrastructure. And then we have talked about the management aspects of this infrastructure, like again, at a very high level. Again, the goal of this talk is to not give a summary of all the works that have been done in this area. It is more to raise interest or to add some initial insights into what it is that we're talking about, and whether these are like fully addressed problems or whether these are still right in the work, where it gives right researchers in the field some more problems to actually tackle, some more realistic and practical problems to tackle. Okay, so this is the next is going to be on the cloud computing infrastructure. So before I go to that section, I would like to pause and see if there are any questions. Hello, anybody there? Any
Yes, sir.
questions? Yes, please go ahead. Yeah. Any questions or clarifications based on what I said so far? And also, I mean, you can give me feedback, because I am a little bit fast on these topics, because I presumed that, you know, these are kind of by now commonplace for computer science teachers or IT teachers in the field. So if it is too fast, then I'll go a little bit slower, but I'll still finish within the time. And also time, could you please tell me the end time? I know it says 12 o'clock, but is 11:30 or so all right? I mean, I have 120 slides, so we can go that long, but depends on what the interest levels of people are.
It's okay, sir.
Okay, okay. Let me see how far I can go before I get exhausted, because most of you are listening. And let's see. Okay, let me just stop video for a little while, if I can get the system to cooperate. Okay, so that. All right, so let me continue with the 5G cloud computing infrastructure. So we have seen what the cloud is and what the infrastructure challenges are in running a cloud. Now, right, over the years, we have started looking at right 5G networks. So probably I heard enough of news, of course, with the current COVID problems, and with most of us work from home and online meetings and online right sessions such as these. The network is, you know, the wired network, wireless network has become sort of the crucial component. Unfortunately, in India, even now 4G right adoption is not that widespread. I mean, even in say in Chennai, there are not many places where you can get very good 4G coverage. Things are good, but like, you know, in large metropolitan cities, I think 4G coverage is all right. But even that varies by building, varies by location, by floor, etc. So in the meantime, people have been working on 5G technologies, which has been in the works for a few years now, right? And so let us talk about 5G. And the reason I picked up 5G in the context of cloud infrastructure is that this is a DOT funded project. And DOT has given about 240 crores to about 10 institutions. Many IITs, about 6, 7 IITs are there, and Indian Institute of Science, and a few other CSIR labs are also involved in this. Plus, of course, the company partners who are interacting with us on their own time and money. Okay, so this is a 3-year project that started 2018, and it's supposed to end sometime in middle of 2021. So that's the reason why I took 5G, but also because 5G has now evolved into a system that is a natural application of cloud computing. Okay. So in terms of a little bit about 5G, just to sort of see why the requirements for cloud etc. comes in, is that there are so the expectations is that these all of course the sort of pie in the sky expectations. All of us want this, right? All of us want 1 gigabit per second on our cell phone. Okay, but will it really happen? Maybe, maybe not. Okay, so some of the things are like the amount of traffic is going to be significantly much more, and in COVID times you'll agree that a lot of our traffic is going on the network much more than what it was even last year at this time. And in terms of devices, they're talking about 100 times more devices, and latencies have to be even lower than what we can get with 4G networks. And a lot of other little things are there, but I would say some of the things are right for a given user. If I'm able to get 100 megabits per second on the wireless link, well, that's pretty good. Okay, today if you're lucky, you'll get 100 Mbps through some broadband on at your home, but that is not very common, right? Most of us are even 10 megabits per second still luxury, and 1 to 2 megabits per second seems to be sort of the average. And there are plenty of pockets of coverage where even 512 kbps is still is what is available, and we get this feedback from students who are taking our online courses. Okay, so so this is the sort of general flavor of what 5G is supposed to do: higher data bit rates and sort of lower latency, and a large number of devices to be supported. So there are different type of applications that are coming up in the 5G context, right? Which are going to be placing a big load on the system. Okay. So one is called enhanced mobile broadband, which is basically our sort of broadband connections are taken to a different level. And then we have Internet of Things, which is called massive machine type communication. So there are a lot of sensors deployed across a large city, and they generate data in large numbers. Okay, each sensor might generate only a small amount of data, but collectively with maybe millions of devices in a smart city, the total volume of data can be very large. Okay, then we have the other extreme, which is called ultra reliable and low latency communications. For example, self-driving car, right, is really dependent upon a very, very low latency and also high reliability. You cannot afford to miss a packet. If I'm driving a car, you cannot say I crashed into the car in front of me because I missed a packet, right? The packet was dropped by the network. So these are sort of the various sort of scenarios where applications are there. So one of the things that people were designing 5G was to consider, that the network demand can be highly elastic. Okay, the network demands can vary quite a bit, which is different from what you see in 3G and 4G. In 3G and 4G, you probably can predict the total load on the system on a daily basis. But with the 5G systems, the expectation is that the load can vary quite a bit, and therefore we need to have infrastructure that can carry such a load. Right, infrastructure again, some of it is physical, some of it is built out. You can go build a base station, okay, but suddenly a base station does not have enough computing power because so many connections are coming in. Then what do you do? Right, so there is going to be an infrastructure design that combines hardware, which is fairly strict, right, which is fairly rigid in terms of the end, right, closer to the end user, but then the behind the scenes hardware like your data centers etc., there you can have a lot more flexibility. You can have deploy a lot of data center kind of servers, and then keep adding servers as the network load goes up or down. Okay, so in terms of where 5G standards we stand, right, again this is a very confusing diagram, but all it's saying is that the release 16 sort of is now ready in 2020. Not all components, still some components are not completed, but release 16 radio access network part is complete, and release 17 work is already started and is going on. So there are a series of releases 16, 17 and 18 that are being redefined. So what is the key objective? Like I said, one is to provide a flexible platform in terms of the system capacity, right? And second is it is going to be virtualization based, like the techniques we talked about before. How can I bring in 5G and virtualization? We will see that shortly. It should be cloud friendly. It should be programmable. It should be stateless and scalable. Right? These are all the very high level design goals for 5G, which clearly implies an infrastructure that is able to cope up with all these requirements. By infrastructure, I mean both the base station and the wireless infrastructure, as well as the computing infrastructure that is doing a lot of number computation behind the scenes, okay, between the end user and the the system. So we'll see what that is like. Okay. So some of the key concepts is the first is cloudification of the NG-RAN and 5GC. I will talk about these terms shortly. And then also if software-defined networking comes into play, and what's called service-based architecture is also there, and network slicing. So I mean, this is a little bit too much detail, but I just want to put this slide to say that you can see that a lot of this is based on software. Okay, if you see that this is pretty much based on modifying the software of the system. On the hardware side, yes, there are a lot of changes in terms of radio access technologies and so on, but there is significant amount of software that is going on that is behind the scenes. And how does 4G and 5G differ? So in 4G, you buy the, say for example, Ericsson, right, sells you and the base station and the corresponding, right, backend servers that go along with it, what they call, right, HSS units and so on, right, units and so on. So these are essentially hardwired systems that the vendor sells you, both the end hardware as well as the software that goes along with it, and they are not exactly scalable or programmable, etc. Okay, they are configurable but not highly programmable. But when we started looking at the 5G world, it was a design decision to make sure that the system is more flexible, like I said before, and therefore a lot of things are going to be done in software. Okay, they are not going to be done in proprietary hardware anymore, but they're going to be run in software that can run on generalized hardware platforms. So that is a big difference. And that is where infrastructure comes in and plays a big role in the success of 5G. Okay, so like I said, 5G talk itself can go for hours, but we can skip that for now. Okay, so there's a lot of cloudification of data processing, right, that happens in a 5G network. So where does it take place? In the radio access network, the packet core network, the mobile edge, all these places. We'll talk about some, we'll show you some diagrams that actually explain these things. And a lot of the performance issues where, because once you go to cloud-based, software-based processing, right, latency, throughput, scalability, reliability, all these start coming into play. And how do we achieve this in software? Right, with all these guarantees. That is the main goal of designing such a system. So the system 5G network looks something like this. You have end users, right? It could be cars, it could be mobile phones, it could be drones, right? Internet of Things, or some, right? Actually, finally, we can even look at desktops systems, right? And laptops and iPads and so on, which are communicating with the so-called access network, which is the radio access network. And if you can see, this is our traditional, right, base station tower. So what used to be right behind the tower was again proprietary hardware. Okay, but now all that is being replaced by two clouds, three clouds, in fact, between you and the internet. So between the user and the end internet, there are actually three clouds that you may be interacting with. One is called the radio access network cloud, where a lot of processing takes place. And one is called the edge cloud, which is useful for many applications. Mobile edge computing, again, is a topic on its own, right? And that again will take a whole a couple of hours to cover. And then you have the core network, which is the one that does a lot of other, right, processing of your data packets. Okay, so your packet will go from the user to the RAN cloud through the base station tower, and sometimes to the edge cloud and go back, or sometimes it will go to the core cloud and then it will also go to the internet. Okay, so this is sort of the sequence that your packet goes through. So the next generation radio access network provides a last mile connectivity, right? And there are two components, user equipment and the base station, or G0B as it is called. And then there is a 5G core architecture, which does a lot of processing to actually handle and forward your packet to the rest of the network. Okay. So the radio, the G0B itself is actually composed of three components, right? Radio unit, and which is the actual hardware, the radio hardware. So that is not our concern, so we will skip that. But we will have other things called distributed unit and a centralized unit. And these DU and CU are basically cloud centers. Okay, these are not hardware units. These are essentially data centers which will be deployed, right, somewhere close to cell sites or transport aggregation sites or even edge sites. For example, I can put it in a central office. I can put it right in every Chennai city might have a few edge sites all over the city. And of course, cell sites, we know where the towers and rooftops, etc. are. So these are software, right, computing resources that are going to be deployed in many places. And that forms the 5G computing infrastructure. Okay, so the system kind of sort of looks like this. Radio units go through a mid-haul network, and then they connect it to the NG-RAN, which in turn is connected to the backhaul network and goes to the core. And from the core, we go on to the internet. The same diagram, right? So now it's showing that these are now, right, essentially the distributed unit that I talked about, centralized unit I'm talking about, all of these can actually be realized with a virtualized infrastructure that essentially contains a data center. These are servers that will run various computations that are required for processing the user data. Okay, user signals are actually going to get processed, not just the user data packet. Even the 5-layer signals will get processed at these data centers. That is a big difference with respect to 5G and the infrastructure model. And then the core network is, we'll talk about the functionalities later on for the core mobility management, right? IP data forwarding, IP addressing, all those things will come into play, right? Yeah. And so again, this is a virtualized environment where there is a computing, storage, and networking, which are then connected via, right, VM or container, to which are sort of supported on a VM container, and then packets go to the data network. Okay, so now there are a lot of protocols that even at the end host, right? So these are all various protocol functions. Okay, so this is where this notion of functional virtualization comes in. So each of this, if you normally see, is if you look at a Unix machine or a Linux machine, right? These will all be, part of the kernel, but this will still be functions or modules that are written which will run directly on the kernel. So what the 5G model tries to do is it tries to execute, right, parts of these functions in the data center. That's what is happening here. Okay, this is the controlled plane stack. Again, a whole bunch of protocols are there. So when it goes to the cloud, right, some of the lower RAN functions are implemented in the DU, and some of the higher RAN functions are implemented in the CU. By lower and higher, I mean, right, so this is the lower part of the RAN stack, higher part of the RAN stack. Okay, so these are functions that will be deployed in these distributed unit and the centralized unit. And there's a transport network that connects all these guys, which carries data of the order of about 10 to hundreds of gigabits per second. So for example, here in this diagram, this mid hall, right, is what we're talking about. There's a front hall as well as a mid hall, right, which carries a lot of data, right, of the order of hundreds of gigabits per second to do all the processing. Okay, so between the RU and DU, you can have some fiber, and between the mid hall and the DU and the CU also, you can have some fiber optic network that carries lots of data. So that's what is basically happening here in the context of infrastructure. Okay, so if you look at the network, it looks something like this, right? These are all, let's look at the 5G network here. So there are radio units. These are all the towers. Many of them are connected by a fiber optic, right? Fiber to a distributed unit, which is then connected by a switch to a mid-haul network. And the mid-haul network is connected to a centralized unit, which is where another data center is shown here. And then this in turn connects to the telco cloud, right? Which this is the packet core. So you can see there are lots of places where computing is distributed. The DU is here, the CU is here, and the packet core is here. So all these are infrastructure that are necessary for supporting the overall 5G network operation. Okay, and the interconnections between all of this, there are various types of interconnections, right? Ethernet, carrier Ethernet, or even fiber optic network is also possible for carrying this kind of traffic, and the data rates can be very, very high. So this is sort of the computing infrastructure that makes up the so-called, right, 5G network. So if you look at it another way, this is what actually is happening, right? Let's try to analyze this diagram. It's kind of complex. So if I look at a data center, which is right running, for example, the DU or the CU, okay, you can see that underlying hardware as usual. The OS is there. Then there's virtualization technology, could be whatever containers or virtual machines, and these are various functions, right? So for example, CC22 is a function that corresponds to user, and so all these colored bubbles here indicate different functions that are being run for a particular mobile. So for instance, you will see that mobile user 1, mobile user 2, mobile user D is there. So for each of these users, there's going to be an instance of the corresponding function. So this is RRC1 is basically a function running on a core, right, which is supported with underlying hardware. So these are all, right, core that are, these are all core functions, right, or sorry, the RAN functions that are being supported with the underlying hardware for implementation. And this is how actually you're going to realize a particular system. So you're going to have a distributed unit and a centralized unit, which will have multiple cores for computation as shown here, right? Multiple cores are there, and each core will execute a single subfunction at a given point in time. So it's a very complex network that we're talking about here. And so since the team is coming back to the infrastructure management, right? So there are a lot of challenges here in terms of achieving, assigning the best available core for a particular subfunction. And remember, this is operating in real time. Okay, you are making a call, okay, and some part of your signal processing is actually happening at a remote location. It is not happening at the base station tower. It's actually happening a little further away in a DU. Okay, so how do I do these real-time functions, right? So look at this, the time budget available for doing computation, right? So the data is coming from the radio resource head. it's coming into the DU and the CU. Okay, you have about 2 milliseconds when the user wants to send a packet to do all the processing, and 1 millisecond when the base station wants to send a packet to the user. So you're talking about really, really tight timelines. And how do I achieve this, right? How do I manage this infrastructure? Now the question is, so here, as you can imagine, there's a lot of optimization to be done. Which user goes where, which function gets run on which core, right? All these things are going to be really, really critical. And to do this efficiently, remember the three techniques we can do: naive techniques, heuristic techniques, machine learning techniques. Now the question is, can machine learning play a role in this kind of environment, in this decision making, in the resource allocation? That is one of the problems, right? There are many places for machine learning to be used, but this is one such possible place where I can use to enhance the overall performance of the system. Okay, so here is again what I said. And yeah, I'll just skip this. So if you look at the core, so that is the RAN part, right? So we said that the RAN is connected to the core, and the core has a lot of other functions. Okay, I won't elaborate on all these functions, but essentially the UE, right, talks to the RAN, and from the RAN, all the signaling part, there's a lot of control and signaling data. Okay, that is what is happening here. See, if I generate a data packet on HTTP, it goes on the user plane function to the end user. This is the normal data traffic. But then to set up these connections and use these resources, I have to go through the control plane, which processes a lot of the control functions. For example, I register myself, right? When you turn the phone on, your SIM card has to be registered with the network. How does registration take place? That takes place in the control plane, right? And again, you want to establish a session to talk to the rest of the network. That session establishment also has to be done. Okay, and as you're moving around between different base stations and cells, how does your data get transferred from one cell to the other cell? There is again some control information that goes on behind the scenes that ensures that your messages are being transferred as you go from cell to cell. Okay, so therefore there is a notion of a user plane, which is a normal user data traffic, and a control plane, which does all the behind the scenes control management, right? All the control functions and signaling functions are going to be handled. So if you look at the system, it is again designed explicitly as a bus here. This is not a real bus, but this is like a communications bus, more like HTTP protocol that's going to run interconnecting these various functions. Okay, so some of the important functions, right? AMF, access mobility management function. So this is the main function that the user talks to. So when I register, I talk to AMF. AMF talks to these various functions. Each of them has a particular role, and then it establishes you or adds you to the network, saying that you are a valid user. You are hereby authenticated and authorized. Okay. And for that, it has to go to this AOSF, which is the authentication server function, which looks at your secret keys and computes some secret keys for further communications, right? All those things are there. Then once I establish myself, I need a session for actually transmitting data packet. It's called the PDU session. Okay. And that is again handled by the session management function. Okay. So in summary, the data that the user generates, right? Some of it goes through the user plane. Some of the packets go to the control plane for processing. Okay. And each function has its own particular role. Now this model, right, is called a service-based architecture because you have different entities offering services which are combined together to form an overall core network. So then I take this now, right? I can take these individual functions of the 5G core and actually run them using this notion called network function virtualization. So what is NFV? NFV is nothing but, right? Instead of running a function on a dedicated hardware, I can make it into a virtual network function, which is simply a piece of software, right? That's all. It's a program which I run in VMs and containers. Okay, so this gives me flexibility. For example, if I want 100 instances of AMF because the network load is very high, I can easily do so. I can span 100 RAID copies of the same network function for doing this particular AMF task. Okay, that is the basic idea of what NFV does for us. I'll skip this part and go back to that. So in essence, what you have is, right, again, these different network functions are running on top of the same virtualization infrastructure that we all know about, right? There's a compute, storage, and network, and these are all different network functions. So when a packet arrives, it will go through multiple network functions, like I said before, right? It can take this path and go from endpoint to endpoint, or it can take some other path through the network and reach the endpoint, okay? So the network is now defined as a set of functions, right, like our C programming functions that are run on these virtual containers, right, virtual machines or virtual containers to deliver whatever services that the application requires. Okay, so now what we do is the same NFV model that we saw, the 5G service architecture that we saw. I can run each of these functions as um, virtualized functions that are going to be run in virtual machines or containers on the cloud. This is how my cloud is now important for even realizing the 5G core, right? So all the core components are software functions, and they can be stateless. Therefore, I can create multiple copies, and I can also move a particular instance of a function from one server to another server because there is no state being maintained. And I can virtualize it and run in VMs and containers that are there on the cloud. Okay, so therefore, now the cloud again comes into a big role, just like we saw in the data center, how in the RAN, how different functions can be run on a data center. Likewise, in the 5G core too, we can run different functions in the data center using VMs and containers. This is kind of the same diagram, but there are other things called MANO, which is, so we need some sort of entity that manages the entire operation. That's called the MANO framework, the management and orchestration framework, which basically takes care of, right, when do I create an instance of a virtual network function, right? And when do I collect, how do I collect data statistics from the network function on a regular basis? And now also we look at what is called, right, DAF, network data analytics function, for providing all the analytics. So in summary now, what we have seen is that the data center concept that we saw before is applied in a big way in the context of core, in the context of the access network also. It is also applied in the context of mobile edge computing. With that, the first part of the talk will kind of get over. So what does edge computing mean? Edge computing means that, see, right now what happens is, right, if you want to get some data, right, it goes all the way to some server. For example, Gmail. Gmail, there is no server in India as far as you can understand, right? So you have to go to some server in Singapore and fetch the data for you. And if you're trying to do some image processing or something like that, right, it is not always possible to go to a remote server and get the data. The delays are fairly high. So therefore, why don't we add some computing resources which will have some of this database, for example, image recognition, right, software. So you have a bunch of database of images that you want to check. Why don't you put that database source close to, for example, your base station or close to a central unit, right? Close to the user than to some remote internet location. That's all mobile edge computing is all about, right? It's basically moving the computing, storage, and network resources for some applications close to the user such that you can support low latency and mission critical services. For example, you're doing automatic driving. You need automatic rate processing of your images because you are simply having a bunch of cameras tells you what the world around you looks like. You need some map information, you need some road information. All of this has to be done in real time. Okay, so therefore, mobile edge computing simply moves some of these computing resources closer to the end user, such that I can handle poor or intermittent network connectivity, and also I can provide much lower latency, and also it decreases the volume of data that I send across the RAN, the backbone, and the cloud. Okay, so rather than send the same data all over the world and then it comes back to you, if I put a local server, I can cut down on the processing latency as well as the computing resources as well as the network traffic. That's the basic idea of edge computing, which again is going to be done with data processing at the edge. Okay, so a lot of applications are there. I'll just show you the basic system, what it looks like, and then we'll move on. Okay. So, for example, different applications that can benefit from mobile edge computing, right? So, like I said, smart driving, I can do all the processing I need for smart driving with some local edge cloud that is sitting closer to these end users, right? I can build a smart energy grid again by doing all the edge processing, right, closer to the user than taking it to some faraway location. Smart cities, right, around UAV networks also can benefit by talking to a local network than to some remote network. Okay, so what does the network actually look like, right? So the same scenario we saw before, slightly different, right? So there's a UE that we saw before. A distributed unit is here. Control, the centralized unit is also here, right? Now what will happen is before some packet goes on to the rest of the data network, right? So packet can go from here to here data network. Some of the packets can be routed to the local edge cloud, which is here. There's a cloud infrastructure again here on which there is some MEC platform and some applications running. So this, for example, could host some image processing application. Image processing data is stored here. So face recognition, I can do locally. Okay, I want to do some map processing, I can do that locally. So these kind of computations I can do close to the edge. So say 20% of traffic is routed to the cloud because I can handle it locally better, and 80% goes off to the rest of the network. Okay, depends on the nature of the application. Some applications, for example, you might want to keep a copy of your most used Gmail, right, data here, or even content data set providers, right? They can store, for example, you're watching the latest movie released. There is no point in going to a remote server to get all the copies of data. If this edge cloud, right, is also some of is in cooperation with the service provider, I can store, just like caching, right? Most of you know about caching. I can store, say, some recently used files on the edge cloud such that my latency is reduced. I simply go here, fetch the movie contents, then go into a remote data network. Okay, so essentially that's what this edge computing tries to do. And why do I bring it up here? Because again, the right whole thing, there's a cloud infrastructure here. This is also a data center that is going to store data, store, right, as well as will provide you computing right resources. Okay, so this is again getting very popular. In case you have not seen IBM, Microsoft, right, all these folks are big on edge cloud because they see a way where they can deploy their services here, and they can tie up with AT&T or with Airtel and so on to build edge cloud services that anybody can use. Okay, so you will pay a price for it, right? If you want data from a remote source, fine, you pay less data. You want something from closer to home, you will pay a higher price for it. Okay, and there will be a lot of applications now that will be right edge based than cloud based, right? We are used to cloud based applications, but so slowly you will find that there will be more and more edge cloud based applications than remote cloud based applications. Okay, so this is sort of what I wanted to set the stage for in terms of where does infrastructure come into play, cloud computing infrastructure come into play in the context of right data center, in the context of 5G networks. And so recap, so cloud-based infrastructure is used to implement many things: RAN processing, core processing, mobile edge processing, and we need efficient management utilization of cloud resources, right? That is infrastructure management. How do I do this efficiently? I should provide the users good quality of service. I should provide high aggregate and device throughput, low latency, and the cloud should be scalable, elastic, flexible to meet the dynamic traffic demands. So these are all right. This is question asked today by right Ericsson's and all the others too. And the question is, can AIML techniques help us achieve this particular set of goals that we are putting down? Okay, so I'll take a break here for about 5 minutes or so, and then we'll continue after that. Before I take the break, any questions?
Excuse me, sir. There is a question posted in the chat.
Okay, let me see that. Which performs data processing important? Okay. As we are aware of cyber attacks, what the data is sniffed between the RAN and the destination tower will create discrepancy in data. Okay, let's see what happened in the right networks. That's why I talked about the authentication server function. So most of the data that goes between the end user and the base station tower is encrypted. Okay, so the SIM card that you have, right, that will generate some using that we can generate some keys for the communication. So every time you go through that AMF, right, it talks to the AOSF, and a set of encryption keys will be created and used for that particular session. So therefore, sniffing on that will not help much unless they're able to break the encryption code, which is very difficult. So that part is taken care of. Whereas if you look at Wi-Fi, right, Wi-Fi, we have to be more careful because Wi-Fi, many of us don't have encryption turned on. Okay, that you should be more worried about because, right, because many of us don't use passwords for Wi-Fi. We simply allow free login. And that kind of scenario, right? And if you're not enabled web or WPA, then the traffic going on Wi-Fi will be unencrypted, right? Okay. Another question is from K. Sheila, who says that technology involved in Industry 5.0. I am not the right person to answer that. I've not really looked at in Industry 4.0 or 5.0. I think that will be somebody from a smart design or smart manufacturing who will be able to answer that question. So I will have to defer that question. Sorry. Okay. Okay. Thank you. So let's take a 5-minute break. It's been an hour since we started, and then I'll try to come back and sort of finish the remaining. So far, all I've done is establish that infrastructure is an important component. Now we'll take a little bit look into where whether AIML can play a role or not. Okay. Okay. So by 11:05 we will reconvene. Thank you.
Okay, sir. Participants, you are kindly requested to stay online since he will come back after a short break. Thank you.
Shall we start?
Yes, sir.
Okay, ma'am. Thank you. Hope everybody is back from the break. All right. Okay, so next I'll talk about the test bed briefly on about 3-4 slides, right, to sort of put perspective to what we're trying to do, right, and how we're actually realizing it. So the India 5G testbed is, like I said, funded by the Department of Telecommunications, and the lead institution is IIT Madras with Professor Bhaskar Ramurthy as the technical lead, overall lead. And other institutions are CIVIT, which is Center for Excellence in Wireless Technology at IIT Madras Research Park, IIT Bombay, IIT Kanpur, IIT Hyderabad, and Samir, which is an METI lab, and IIT Delhi, IISc Bangalore, and several other Indian industry partners. And if you're interested, the details are at 5G in the website listed there. It is kind of under construction. It's, I think, the beta version that's out right now. So if anybody is interested in actually, when this is for those who want to do research or actually development work, this is a good opportunity. Of course, the project is only going to be till mid-September right now, but there may be other extensions of this work as we go along. Okay, so what does a 5G testbed actually involve? So it's essentially involving building the entire system from scratch. Okay, indigenous system, and all the algorithms, everything is sort of built from scratch with the help of hardware and software that we have to buy. I mean, for example, we use FPGAs from Xilinx, and we use, of course, servers from various companies such as Dell, etc. But other than that, right now, the entire code base is all from scratch. We are not taking any existing software from Ericsson or anybody else, right? So it's built by us, by the various teams. So we are building the user equipment, then we are building the radio resource set, which is the one that sits on top of the base station tower. And then we are building the antenna. Also, the MIMO antenna is built by Samir. And then there's a front haul communication, there's a fiber communication, right? That's based on CIPRI standard. So we are building the BBU, or the baseband unit, which is got the DU plus EU right functionality is here. So the RR is only the radio low level 5 functionality, and all the higher 5 layer and higher layer 2 functionality, MAC and above, are handled by the BBU. And then there is a backhaul network which connects to the mobile core, which is the one that I talked about so far, the SBA based 5G core. Okay, this is the system architecture. And if you look at what actually the system contains, like I said, right, these are all FPGA based devices. So the UE is going to be a board actually being built with some of the code, UE code, running on FPGAs. And likewise, the base station is also being built. This is at base station is built at IIT Kanpur. UE is being built here at IIT Madras and also in IIT Hyderabad. Then we have the antenna is being built by Samir, right? So all of this will then communicate wirelessly to the unit, which has, sorry, this is wireless, but this is your front haul eCPRI. And this is where the BBU is also another layer 2, layer 3 card, which has got sort of regular computing system plus FPGA for doing fast processing. Remember, we use FPGA because we have severe time constraints. I mentioned the 1 millisecond, 2 millisecond time constraints. So a lot of the challenges are there in achieving this sort of right very, very strict time constraints, almost dire time constraints, I would say. And then we have the 5G core, which is simply run as software unit, right, in a set of servers that we have at IIT Madras. And it's possible that next couple of months we'll do some demos through some conference like CompsNets and so on, where you can actually see some of the core demo in progress. Last year in 2019 October, we had the Indian Mobile Congress in Delhi. At that time, we demonstrated some of the hardware components actually working there in the demo. The minister had also come, and for INB as well as METI. And of course, so the core is also being built right in the overall system. So this is kind of, again, to put it right. So the computing infrastructure here is mostly on the FPGA side, but this is pretty much what we talked about before in terms of the network function virtualization is implemented, as well as the other related components are also there. So the core functions are implemented in servers, in data centers, and This is normally going to be if it's in real network, it'll go in the data center of the service provider. And right now, the 5G core team that we have in our group is CIVIT and IIT Bombay, as well as IIT Madras. Okay, so this is just a mini plug into sort of show that we are actually looking at using these ML techniques in our test bed. So far, the focus has been on functionality in terms of realizing these functions. Building the software units, but then now we are going to look at whether ML can play a role in this test bed. That's how I got into this into this whole environment. Okay. Sorry, it's kind of not behaving what I wanted to. I wanted to turn off video. Okay. All right, so let me tell. Okay, so ML overview. Again, some of you might actually be teaching machine learning courses. I'm not a machine learning expert per se. I'm still on the way. I mean, I did probably pattern recognition as a course when I was a PhD student, and that was about 30 years ago. So I'm trying to understand, right, what the techniques are. Again, there is a whole slew of techniques out there, and this is just to show that there are so many possible techniques, right? And one of the challenges in networking is which of these will be suitable for networks, right? For infrastructure in particular. And since my area of research is mostly networks, I'll be focusing on the networking component of things, right? So there are lots of these popular machine learning algorithms which you can find today in various courses and right in various software packages like PyTorch and others that let you do these things. Okay, so again, very quick introduction in case some of you are not aware of the terms that I'll be using. Right, so there are many tasks that machine learning can be used for. Some of the common ones are clustering, where I try to group similar data points into two clusters, right? So this is cluster one, this is cluster two, or classification, right? Where I would like to know whether a particular item belongs to which class, right? Class one or class two, and so on, based on the data. Or the other is prediction, which is called regression in machine learning terms, where I'm giving a set of points and I try to sort of map a curve that more or less matches these data points, so that I can use it to extrapolate and find out for some unknown value of x. So these are known values of x and y. So for some unknown value of x, what can be the value of y? Or I can predict something in the future. For example, if this represents load on the network, then what is the future load on the network? I can predict using regression techniques. And also rule extraction, which I won't talk much about. So the basic task is to classification. Again, it's a quick intro. Excuse me. So in classification, the idea is to divide the data into a set of classes based on different parameters. And this is suppose training data, and then figure out what the classes could be. For example, if it's a binary classification, then I'm given some data, some of which is normal data and some of which is anomaly data. And somehow I have to figure out from the data characteristics, right, how to build a model that given and some unknown input item, whether that is right in the normal category or in the anomaly category. There are a lot of classification algorithms out there, which is briefly listed here. If you find any errors in this, please let me know. I'm still in the learning process. Okay. And machine learning techniques for task of regression, right, is again to find a correlation between dependent and independent variables, right, is normally done with what's called as curve fitting, right? And for example, I can predict market trends, housing prices, or if I want to predict what will be the call holding time for a particular session, which will, for example, virtual data center request comes in, how long will this data center be, right, alive? Because I have to allocate resources for the time duration. So that is one. Or I can try to predict the number of mobile users in a given network at a given point in time. Right. So if I, based on my past history for let's say 1 year, I know that in this given cell tower, there are 100 users at 8 a.m. in the morning, right? Every 8 a.m. every day. Then can I use some sort of, can I build a model that predicts, right, tells me what will be the number of users in a particular cell at a given point in time, which I can use for some resource allocation, right, decisions. I can maybe give it some more channels or some more resource blocks, etc. Right. So there, again, regression is a whole slew of regression algorithms. So I'll not go through them in detail, but a lot of possibilities are there. And so in general, if I sort of summarize, I've only given a couple of samples there. So the basic idea of how an ML-based system would work is, again, right, so there is data collection, and if there is an expert, if there is some supervision that is required, right, some labels can be supervised, or it can be semi-supervised also, right? So essentially data collection is there. You select the features that you would like to, you have to basically, you might have end up, right, so having thousands of features. And the question is which of those features actually capture the behavior of what you're looking for. So different features can indicate different behaviors. And therefore feature engineering involves selection of the right set of feature vectors, and then running it through so the actual the learning of the model, which can be used with one of these techniques that I listed before, right? And then you essentially build a model of the network. So that is the sort of data flow that you do the training phase. Then in the actual usage phase, right, testing phase, you will have some new data that is come in, you process the features, and then you run it against the model and look at the outcome. And then that is, again, you can always do validation of that data, right? And then feedback to the overall data collection process. So this is something in a network, for example, you can do. So consider a network that is trying to look at packet duration or flow durations. I can have long-lived flows or very short-lived flows, right? And depending upon the nature of the flow type, I can give different resource, different routing, for example, whether it's a large flow or a small flow. And let's say that I have some classification algorithm that tells me by looking at the first few packets of a flow, whether this will be a large flow or a small flow, right? And if I make mistakes, if I classify a large as a small or vice versa, then I can always look at the subsequent behavior of that same network flow and then validate against what I predicted. And then I can then go back and change my model such that, some mistakes I had done. So I can rebuild the model based on this sort of feedback loop that I have in the system. It is a general sort of how an ML based system would work. And again, I'm continuing with the background, right? So that supervised learning, unsupervised learning, and reinforcement learning are some of the three classic sort of techniques. And again, I will not elaborate much on this. This is also sort of textbook material. I just want to put this in here for the sake of completion. Okay, we'll see what is applicable in what context for the different networking problems. That's what our goal is. Yeah, these are techniques exist, and these have different applications in many domains we have seen so far. But in the context of the networking, right, especially in the context of networking for real networks such as the 5G network, then where will I go and apply these techniques, right? Okay. So reinforcement learning, I think I'll skip this fairly. I think it's too introductory. I wanted to remove this. Okay. So that's the two the terms that we are going to see is, right, we'll see a lot of these classification and clustering techniques. You'll see a lot of DRL also, right? Deep reinforcement learning. So deep reinforcement learning is again taking the reinforcement learning approach. But what happens with reinforcement learning is that, right? So reinforcement learning is sort of like a feedback-based learning where you have you take some particular action on the system state, right? So this represents as sort of an RL system where you look at the system environment and there is an agent, right, that observes the state of the system at time t and then predicts or suggests an action called AT. You take the action, then the system state changes to something else, ST+1, right? And there is a corresponding reward taken for, right, the action at time t, which is RT. So based on your understanding of what the reward of time t and what the state of the system was, you generate a new action to be taken. So then if that action then again influences the future reward of the system and the future behavior of the system. So the agent keeps learning, right, as to what should be the right action to take, right? So there could be a set of say 100 actions to take at any point in time. And for a particular system state, I can tell as to you should take this action. For example, if you're looking at load on the system, right? And so action could be, for instance, create a new instance of a virtual function. Right. So I'm monitoring load of the system and I find that the load on the system is very high because not enough functions are available for processing the incoming requests. So then a particular action could be increase the number of function instances by 1, or could be increase number of functions by 10 because the load is gone so high. Right. Then you subsequently keep monitoring the system behavior at that point in time and find out whether that extra one function that you added actually made a difference to the system behavior by measuring the reward. And if the reward is right, if the system is actually rewarding you for taking the action, then use that to build your model. That's the basic, right, concept of RL. So RL again has been used in many toy robotics examples, but it's a fairly complex system because as the number of parameters and variables increase, right, it's like a sort of an optimization problem where it's not scalable, right? So what people have figured out in the last few years is that I can use something called deep learning, where I can use neural networks to reduce the dimensionality of the space, right? So with that, I can go for lower dimensional feature representations. So therefore, DRL is right, is a sort of a common term that we would see, a common technique being used in many of the systems that we have looked at so far. Okay. So DRL has a lot of applications, right? People have used it in many systems. Of course, we are not so concerned about education or transportation and so on, but people have been trying out many things, right? In robotics, computer vision, NLP. But what we are trying to look at is this particular notion of computer systems in resource management and performance optimization, right? Whether DRL can play a big role in terms of right, providing us sufficient benefits. Okay, so we'll now sort of focus more a little bit on the recent works in AI, ML, and 5G network resource management, right? Because that's what we said we will do. So before that, right, like I said, there are tons of machine learning, right, possibilities used in the network, and so planning and design, right? For example, this one thing I mentioned early on, right? When I design a cloud center, then what kind of techniques can I use, right? So this is a summary from one of the, I think this is from, I'll put the source here for this one, right? This is taken from one of the papers that I read. So there are different techniques that are possible for different functions. I won't list through all of them, but if you look at the network function classification, planning and design, right? This is the early stages of designing what an infrastructure should be for a cloud center. The second is operation and management, right? Then there is monitoring of the network, right? Is the system behaving well? Is the system, right, underperforming, or is the system, right, towards going towards overload scenarios? That is what monitoring is. And also fault detection. This is also important, right? Is it possible that a particular network link will fail, or a particular server will fail, right, because of some things you're observing? You're having some sensors on the server, and you're predicting that this server is likely to fail. And if it is going to fail, then what should I do, right? I have to build in some kind of right, or the network is going to go into there's a lot of additional traffic is there. So how do I estimate or predict faults in the network, and how do we actually take corrective action so that before the fault occurs, I can actually try to rectify the fault? Okay, and security, of course, is also another, right, very important application of system security is another common application. Okay, so bottom line is there are several possible machine learning techniques. I mean, this is not a complete list by any means. These are some suggestive techniques that one can use, and some of the purposes for, right, each of these for this class of techniques is also listed here. Okay, so this is something that can serve as we can look at this, and then you can, before you decide on choosing a particular problem to work on, you can look at what are these sort of suggested techniques for the particular right, specific problem that you are looking at, and then try to address it using one of these options. Okay, so now as I said, right, the standards bodies have caught on. So the use of AI and ML, right, was in early stages about 5-6 years ago. But since then, right, many standards frameworks have evolved over the years. So one of them is this ETSI, Evolution Network Intelligence Standard, called ENI. And these are frameworks. These kind of tell you how to combine machine learning and how to combine right, network operation. So this is very specific for networking. So there is also ITUT standard, which is talking about a framework for machine learning in future networks, including the IMT 2020. And also 3GPP has its own specification as to how to bring in data analytics right into the overall system. So NWDAF is yet another network function, just like the other function that we saw before. And these are some of the common frameworks out there. The reason we look at these frameworks is, right, before you launch on a particular problem, you can understand what these frameworks are, right, and then make sure that your approach is sort of fitting into the framework. The framework will not specify the particular algorithm, right, or how to solve a particular problem, but the framework will tell you, right, how to put together this such that the basic steps are taken care of. So the underlying like foundation is there. You still have to fill in the application domain, you have to fill in the techniques and so on, but the framework is very useful sort of to capture sort of common sense principles of how to approach a particular problem in this field. Okay, so if you look at the ENI reference architecture, right, so there are two separate sort of systems, right? So this is the existing system, right, which is have these various planes: data plane, control plane, the underlying infrastructure, management, orchestration, service application. This is what a typical infrastructure system will look like today, these various planes of operation. So what they're proposing is there is also going to be a complementary ENI system, right, that has different components, which includes the cognition framework. There's a policy-based management framework, right? What about situational awareness? Okay, that's also taken care of, and context awareness, right? And all of this, of course, we need some sort of knowledge representation scheme that stores this information, right? And as to basically, I have to build the knowledge of this current state of the system using the context of many of the applications that are running in the system. We have telemetry, which keeps track of, right, basically sensors in the system that tell you what the various right status of functions are, what the status usage of resources are, etc. And of course, alarms, right? I mean, system can generate alarms based on something is failing or something is not failing, right? So all those things are basically fed into this ENA system, which represents the operational intelligence of the system. Okay, so this is the system running all the time, and this is sort of like, like an advisory system that is sitting in the background that is crunching all these data, and then it comes up with suggestions and commands as to how to modify the system such that you can achieve the requisite goals, whether it is efficiency, whether it is optimization, right? All those goals are achieved. So this is sort of how the ENI architecture looks at, right, this whole system today. So the ENI vision, right, is if you look at traditional this part of this is right about 10 years ago, you would say that a lot of devices are there, and it was all manual operation and management, right? Configuration of these devices was done manually. Even today, it's still done manually, right? In many cases, if you look at say university computer centers and so on. So you had traditional telecom hardware, which were that sort of rigid hardware, which is not programmable, not flexible, right? So they used to go and manually do the configuration of how the system should be run and managed. Then we moved on to the next generation of systems where they brought in software-defined networking and network function virtualization, which is basically a little more intelligent hardware and software. So now the telecom and software and hardware is based on SDN and NFV. So, but somehow the operation is still manual. When you still have to configure these systems, you have to put in various rules in the databases as to how the system should operate, right? But then what the goal is going into the future is to have again the same SDN NFV hardware, but the operation and planning and data right management is actually based on techniques drawn from AI, such that it is more automated. Okay, so again, this is not new. I mean, if you read papers, you'll see something called autonomic networking, right, about 20 years ago. So the general concept has been there, but has not been really achieved even today. Okay, because like I said, today is still a whole bunch of manual operations and manual right control of the systems. But the next 10 years or so, we should be able to move into a more right AI-based sort of automated system, which has more intelligence built into the system. So that's the goal of this ENA system that we are talking about. Okay. So the ENA document again talks of various use cases. And why I have presented this? This is again for those who want to work on research in this area, right? They have listed, in fact, several interesting problems, right? For example, I will not focus the network operation, right? Let's look at one of them, intelligent front hall management orchestration. So this is a particular problem one can look at and see where can I bring in, what are the functions involved in realizing this intelligent front hall? And in that scenario, what kind of problems can I come up with? And where can I use AI techniques? And then another example is the AI-enabled network traffic classification. Because traffic classification, like I mentioned before, is very important as to what classes do I have, and based on the class, I'll give different priority for resource handling, for allocating buffers, for allocating link scheduling algorithms, right, for giving priority and handling packets. So again, can I use right now there are traffic classification algorithms in the network, okay, but they are sort of based on not AI rules, but they are based on very rigid tables, and right, they take more time to run. So can I use something more intelligent than what is out there, right, to be able to speed up this traffic classification problem? That is one. Then also we come into right service orchestration. So orchestration is deciding how many resources to give to a particular user and how to manage right the resources. And what happens if the network does not right meet certain goals of operation? Then what do I do? So for each of these classes, the ENI system has actually defined a subset. There are a lot more out there in the original document. I only listed some of them here. Okay, so if you are interested, you can take a look at this also. For instance, security is right much more than these 2 bullet points. There are plenty of ways in which I can bring in security and ENI today, right? Which people have done sort of in a piecemeal manner, but putting in a framework helps you sort of focus and also understand how right we can use these various AI techniques. Then the other framework is the ITUT framework, right, which is um, the numbers are Y.3172 and Y.3174. Okay, I'll not go through the definitions here. We'll just look at the architecture here. Okay, so if you look at this system, right? So let's look at this from the layer below. So here is the underlying network. Could be a 5G network, could be a 5G data center, could be a actual right regular data center, and there is the underlying network, and there are several network functions that are currently running in the network. Okay, so what we have to do is we have to see whether the current right underlay, right, which is basically executing all these functions, what is the overall delay in the network, what is the overall throughput of this network, right? So that's what you are basically monitoring. Okay, so then so we have to, so essentially what you have is, right, so you have there is an orchestration and management function that defines how resources are allocated and so on. Okay, so what we do is, right, so we start with right, taking some measurements from the underlying network. Okay, you take some you have some sense or telemetry information, keeps for number of packets, delay per packet, number of packets dropped, right, all those things you would keep track of. And then you have something called an simulated ML underlay network. Okay, so this is like a sort of model of the network, right, where you have a source, you do some compression of data, some pre-processing of data, then you actually do the machine learning, right, modeling of the data, then you do the prediction, right, then you do the actual suggestions, and then you finally see what the effect of that suggestion is. So it's like a two-step process, right? So step one, you don't actually touch the underlying network. This is like a model of the network, right, where you do all your testing, right, all your model learning, and then you can see what happens if I take a particular action. How will it impact the system? So you don't, before going to a real network, you will do this on the simulated model. Then from that point onwards, you will then communicate that information to the actual ML pipeline, which is measuring data from the real network. And then this will then actually implement the various steps of operation, right? So this is the real pipeline. This is a live pipeline. This is a simulated pipeline running on the side. So you try some 4 or 5 options here and pick one option and say the first option looks good. So therefore, let me send that to the actual live system. Then this live system takes the action and makes necessary corrections in the way the underlying network is being operated and managed. And then it'll again have feedback, right? It has to take measurements, and then this process keeps repeating in such a way that your overall system is run as efficiently as possible. That is the goal of the system, right? And this, of course, can apply to any system. It could apply to any production system in industry. It can apply to, right, not just networking. It could apply to any data center or any such complicated system, right, where you have ways of measuring system performance and then feeding it into the simulated ML network and decide on 1 or 2 actions, actually realize the action in the live network, observe the behavioral changes in performance, etc. Then keep repeating this loop over and over again. That is the general flavor of what this is trying to do. Okay, so the details that one would work as researcher is, okay, what is the model here? What is the best way to design a model? And right, where are the sources in this network? What kind of compression should I do? And what kind of pre-processing should I do before I actually figure out, right, what are the set of actions to actually take and realize in the corresponding network. This is again, I'll skip this, it's in the context of, right? So this is how to realize this in a 5G network, right? Where do I, for example, I can put a source in a UE, right, which is taking some measurements, right? And then from that, it goes into, so this data compression part. There are 2 different pipelines here. Let's look at, say, ML pipeline 1, right, where I'm doing some kind of prediction at the at the access network level, right? So this is for latency sensitive applications. Pipeline 1 is for latency sensitive applications, and PL2 for latency tolerant applications, right? So here I'm taking some measurements from the user and then figuring out what should be the access network policy for handling traffic from this particular user using an ML pipeline, right? So then I decide what are the corresponding actions to be taken. So here it shows that 1 to 2, right, 4. So for example, it shows 1, and from here it goes to 2 to another compression entity here or processing entity here, and then it takes some corresponding action, which in turn changes the behavior of the overall network. Okay. Again, this is there are more details in the actual document where this is described, so I will not spend much time on that. Okay. But this is the basic idea, is that I put in sensors in different places, collect the data, do the processing of data at different places, and then send it out, right, for processing, and then implement machine pipeline. This are ML pipelines at different stages of the network. And so I could have one pipeline here for one particular action, right, another pipeline here for another particular action, and so on. Just 1 second, please. So there are a lot of right use cases where one can use. I will not elaborate on that. I'm just leaving this slide again as a potential use case for those who want to work on right how to deal with network slicing, which I have not talked about so far. So there are many cases that the ITUT document talks about. Okay, so this is the general framework, right, as to sort of what to do. And so what are we doing, right, in this space? So we are trying to look at optimization of system or network operational parameters, okay? And the idea is to look at a 5G network like I talked about, and the 5G core in particular. And in a 5G core, right, we have notion of what is called network slicing, where I can essentially create virtual slices. Each slice, for example, corresponds to a particular application. For example, on the same network, I can have a broadband slice, I can have an IoT slice, I can have right a real-time slice, and each of these slices have differing requirements in terms of latency, in terms of bandwidth, etc. So there could be multiple slices. Therefore, the load on the network is dynamically changing. Okay, so how should I deploy these network functions in an efficient manner such that I achieve my main performance metrics, what are called as key performance indicators, despite these load variations? And this has been a low complexity because I need to run these algorithms in real time to achieve my overall input. Okay, so essentially I have a system that is currently running, and I know what the current system parameters are. System parameter means how many virtual CPUs have I assigned, what function is running on what virtual CPU, right? How much memory have I allocated for this particular function? All this defines the overall system parameter and right combination of configurations. Then I also know the performance measurements, right? I have now taken measurements at various points in the network. I know that the delay is such and such, the throughput is so much, the link utilization rate is so much, and so on. And using this, right, the current system parameter and the set of performance measurements, I want to update the overall operational parameters such that I meet some target metrics. Right? For example, I want delay to be less than 1 millisecond. And currently the delay is 1.25 milliseconds. What should I do? Where should I go and change? What should be the parameters that should modify such that I can get the required degree of performance? So there are again many ways of doing this, right? I mean, people have looked at mathematical queuing models, which is very common. People have looked at machine learning models, which is more recently. And of course, heuristic approaches are what finally people end up with, because sometimes the math models can be very complicated. So therefore, you can come up with a simple heuristic, implement that in a discrete event simulation model, and then take that and apply to the real system. This is kind of what one can do in order to achieve these overall goals, okay? So if you look at it in a sort of diagrammatic manner, I have a system which is consisting of servers, VNFs, containers, right? The entire data center components, and operational parameters are fed in, right? That are designed by the administrator, and I measure the output in terms of these various metrics that I indicated, right? So then these are fed into the ML training system, which is basically trying to map it's like a function, large scale function mapping from the parameter combination to the metrics, right? So if I give you 10 variables and some output y, I should be able to figure out what that function is. If f of y is basically f of x1, x2 up to x10, and what is that unknown function f, right? That's what I'm trying to find out through this machine learning training model. Okay, so therefore I build a system model based on that. Then now I find that my metrics are not in the range of what I expect. Therefore, I need to go and change the parameter. So how do I design new parameters? So this again could be done automatically based on suggestions from the system, like I showed before in the ENI model, or it could be something that you can say change, perturb some of the existing parameters to come up with a new set of parameters. So we change the parameters based on the system model. Now this is right. This is live. This is running, but this is a model based prediction. If I change the parameter to something else, what will be the predicted metric? Okay, then I can do multiple combinations of this on the side. Okay, this is a simulated ML model that I talked about, and then come up with finally something that is acceptable from a prediction perspective. Okay, this predicts that these new set of parameters will actually work. So that is what I would pass on to the operational parameters. I will modify the parameters. Then I hope to see improved performance metrics. So this is out of the feedback loop the system is always on, right? The challenge is how do I, right? We'll talk about that shortly. So this is the basic idea. I have a system and I want to keep updating the parameters such that I meet my target metrics. Okay. So what is the problem complexity here? First of all, right, any system will have a large number of system parameters, right? We talked about that before. How many servers, how many cores per function, how many functions. It will be running into thousands of system, right, parameters. So how do I train these models and find out the most optimal set of parameters? That's a feature engineering that we talked about before. Okay. And also there will be several target, KPIs, the key performance indicators, right? For example, if I want to increase utilization, then I might find that latency is also increasing, whereas I want to keep latency to be low. So I have to find out set of sort of non-conflicting KPIs such that I keep everybody happy, right? I cannot always give the optimal solution to everybody. If I increase one user's delay, then the other user's delay will go down, but the first user will not be happy, right? So how do I do this? Again, it's a complex problem. Okay. And so the basic idea is, like I said, parameters to models to measure, right, metrics, and it's a continuous process of learning and fine tuning the overall system parameters. So the different ways of doing that, what I showed before was the sort of machine learning based model. I can also use mathematical modeling techniques to do that. In fact, we may end up doing both, because in some cases math modeling will work, in some cases it will not work, right? So the same thing, I can also build a queuing based network model for mapping parameters to metrics, and then I can run this sort of model on the slide, okay, and come up with modified system parameters. In fact, this can be replaced. Most easy way of doing today is to actually use discrete event simulation, right? If I can build a discrete event simulation with Cloud Sim or something like that, then I know if I change parameter x to x dash, then the new right metric will be something else, y dash, so I can do it on the side. But the problem is building math models takes time, but building a simulation model might take less time, but getting results from simulation model can take a long time, right? You know, if you're running discrete simulation, sometimes it'll take days to get a single point output from the particular simulation model. Okay, so therefore, what we will do is, right, the machine learning model is one approach, but one can also look at other approaches to validate and supplement the basic machine learning model. So this is kind of what we are trying to do in our research at present. Okay, so we are I won't elaborate on this much, but we are trying to look up some problems in this field and try to solve some of them. Okay. And different techniques we're looking at is, one is deep reinforcement learning, and the other is multi-arm bandits, like what's called stochastic optimization approaches. Okay. So there have been a lot of works recently. It's about 140. So another 10 minutes or so. I'll try to wind up. So this is again a summary I left in here more for those who want to work in this field, right? So I'm not going to go through this whole summary. There has been a lot of work in application of DRL for machine and machine learning for networking per se. Okay, so there are a lot of papers that we sort of briefly summarized here, with the goal of looking at network slicing in 5G, right, and where it is applicable. So again, those looking for research problems, right, you could look at some of these papers, find out what is of interest to you, and then take it from there. Okay, so I'll not go through this. This is again a subset only. Okay, we are still in the process of actually putting together a survey article that combines these various papers in one shape. Okay, at that time probably we'll get to see more of this. Okay, so I'll just give one example, right? So we've been talking sort of in the vague terms so far, right? Say yes, ML is there. Yes, we can use it in some places, and yes, DRL is now sort of a popular technique considered for resource optimization. But we should understand that DRL is also very complex. Okay, it is not like a simple heuristic you can make it, right? You can run it and get the values. DRL requires a lot of parameter optimization, and therefore it is not that easy. Okay, so back in 2016, one of the early papers that actually started this field was written in ACM Hotnets, and let's see if we can understand what this problem is trying to do. Okay, so the question that this paper tried to address is, can we do resource management using a deep reinforcement learning based approach? Okay, so can systems learn to manage resources on their own? Right now, you can do heuristics. You can do some simple, scheduling algorithm, etc., to allocate. So let us see what it tries to do. It's basically a cluster scheduler. Okay, and online jobs arrive into the system, and there is no preemption in the system, right? So most of us who have taught operating systems will know this. Jobs arrive, and you want to basically allocate CPU or some resources for that particular job. Okay, And the objective is to minimize job completion time, and several possible objectives are there. Okay, so system overall looks like this, what I showed before, right? So there is an agent. This is the actual system called the environment, and this observes the state of the of the system, which is denoted as S. The agent actually uses a DNN, a deep neural network, for figuring out the parameters, okay, for the actual parameters of interest, and then that is fed into a policy. So this policy is the one that decides for a given state S what should be the action. Okay, so if I take the action, the system takes, you took this action A, the reward for that action is R. So this is a continuous feedback that the system is in, where I take some action. Action A, like I said, could correspond to assigning resources, could correspond to taking some other initiative. In this particular example, depending on what the current state of the system is in terms of resource allocation, I try to allocate which job, I try to select which job to run on the system and what resources to allocate for that job in the system. That is what this paper is trying to do. Okay, so again, this is basically what I said, right, in the DRM model. The system model is basically, I have a computing cluster with D resource types: CPU, memory, input, output, devices, etc. And jobs arrive in an online manner, and the scheduler chooses one or more waiting jobs at each time step. Right, like I said, this is a very easy to understand problem. That's why I selected this. Okay, and this particular objective, they want to minimize the average job slowdown. In other words, if the actual completion time observed in the system is sometimes CK for a job K, and TK is the duration for the job. Right, so the job actually is supposed to finish in 10 seconds, but it took 100 seconds to finish because of waiting for resources. Right, if I had a non-sharing system, I could have finished in 10 seconds, but because I'm using a shared system, it's going to take 100 seconds. Therefore, the slowdown is a factor of 10. Okay, so the overall goal is to see how much can you minimize this average job slowdown. This is the general framework for the problem that is being considered. Okay, so here's the way they represent the system. So here, there are only two resource types. One is CPU and one is memory. Okay, and there are three instances, right, of CPU that is available, and again 3 units of memory that is available. Okay, so let us look at this diagram a little bit more carefully. So the current state of the system, right? There are again the colors indicate different jobs in the system. Okay, so the red job, right, has taken 2 CPU units. Okay, red job has taken 2 CPU units and 1 memory unit for 3 time units. Again, this y-axis is time. Okay, so at one time slot, in the first time slot, the green unit has one memory, green unit has 1 CPU, and the red unit has 2 CPU units. Okay, and also the green job, right, has 1 plus 1 here, so the red has 2, and the red is holding it for 3 time units, right? So the red is holding for time unit 1, time unit 2, and time unit 3. Okay, whereas the purple job is only holding the resource in the time unit 2, and it's holding 1 CPU and 2 memory units. Okay, and green is holding 1 CPU plus 1 memory and only in the first time slot. Okay, this is the general state of the system. Okay, it's almost like Tetris. Those of you who played Tetris, right? So now we have a new job coming in. Okay, so now there are 3 pending jobs. Okay, so this is job 1, job 2, and job 3. Okay, and the resource requirement for these jobs are also shown here. Okay, so for example, this blue job, right, the job slot 1 requires 2 units of CPU for 2 time units and 1 unit of memory for 2 time units, whereas job slot 2 requires 1 CPU and 2 memory for 1 time unit, whereas this guy requires all the 3 CPU slots and 1 unit of memory for 3 slots. Okay, and there is yet another job waiting in backlog. We won't worry about that. Okay, so there are 3 jobs now to be scheduled. Now the question is, how should I schedule, right? Which of these jobs should I schedule at this given point in time, such that I can maximize my overall resource utilization, or in this case, minimize the job slowdown time. This is the general framework of the problem. Because it's an interesting and easy to understand problem, I use this as an illustration. Okay, all right. So now if you can look at it, I mean, I could put this blue job here, right? Again, this blue job cannot start until this 4th time slot, because all the resources are being allocated on the CPU side. So I could put this guy here. I could take job slot, right, 2. There is in the time slot 2, I have 1 unit of CPU free and 2 units of memory that are free. So I could basically schedule first this job slot 2 here and then here. And then in the next time slot, I could schedule this job slot 1 here as well as here, and so on, right? And this process keeps going on, right? So at every unit of time, the goal of the system is to actually solve and decide which jobs can I schedule at what point in time. That's how, right? Now, where is DRL coming? Okay. So, so the action space, as I mentioned here, is right, is to select one or more jobs, and all these things I already have talked about. Okay. So the policy that of taking action, right, is actually represented as a neural network, which is called a policy network. Okay. So the input to this is a collection of images of resource allocation. This is the interesting thing, right? So they've taken represented the overall system allocation as a series of images, and they're using the series of images for the training process to determine what should be the appropriate output, right? So in this case, for example, they output the distribution, probability distribution across all possible actions at a given point in time, right? That's the basic policy. So the policy tells you, like I said, for a given state, what should be the current action to be taken. So using a set of trained images, they decide what should be the possible set of action. Like for example, possible action is to fill, say, the time slot 4 and time slot 5 for a particular job slot. And that's what they have done. The training they have done what is called as episodic setting. I will not get into it, but the bottom line is they have used a series of images to represent the system, right, resource current allocation status, and decide on the scheduling process also. And this is what they have done using their neural network for training as well as for the policy decision. Okay, and I will not get into all of this now that we're kind of running out of time. Okay, they've, again, like I said, multiple objectives are possible, and they essentially show in their paper that I don't, yeah, so they show that they are able to achieve better performance, right, compared to, for example, average slowdown. If you see the blue line is the deep RM paper, which is that MIT paper, and there are other simple like packing algorithms or shortest job first or Tetris, right? Combinations have also been used, and they show that they can actually achieve less slowdown compared to the other systems, and this is done for different objectives also. So the entire code is available. Some of you want to actually play around with this. If you go to his website, the entire code is available on Mao's website for actually running these algorithms. Okay, and our students are currently trying this out. Okay, but the time factor is there in terms of execution time, right? That is still non-trivial, and but you can get some Amazon cluster or something online to actually try out this particular system. Okay, so the website that I want to point it out is okay here. So you can actually go, his code is available on his website. And if you want to try this out for the simple case, and then you can start building more complex use cases based on this. Okay. So this is one concrete example of how to use DRL in the context of infrastructure resource allocation problem. Okay. So they've then moved on to, I'll skip this. Right, then that is a simpler problem. Then they went to a more complex problem where the data is not in that simple Tetris form that I showed before, but it is a more complex what is called a directed acyclic graph. And so we'll show this. So this is now how their different queries are. Okay, so these are different jobs. Okay, what was before just one CPU unit and 2 memory units, they have a much more complex way to specify the requirements. Okay, so each of these represents a query, right, in a Hadoop Spark system. And if you notice, these are all various tasks in the system. So this represents one task. This is 50 tasks currently running. Now there is a directed acyclic graph means that I have to run these 2 tasks, then I can schedule this task. Then I finish. When this one finishes, I can schedule this particular task. And each task requires different duration, different number of resources, right? And also different amounts of data. Okay, the data that is passed between the different nodes, right? So basically I have to run these 2, schedule this, then run this one, complete this one, schedule this, and so on. So I have several such queries in the system, right? It's a very complex data flow graph. And given a set of such queries, and given this sort of complex representation of each query, how do I maximize the overall system performance? That is what this other paper tries to talk about. And that work is called Decima, okay, in their system. So this again, I will not elaborate much on, but they've used a similar graph neural network and a policy network, right? Again, a deep neural network based approach for realizing this. They actually built it and show that the system actually has better performance compared to other similar systems that are already out there. Okay, I think we are getting close to finishing time, so I will not spend much time on this. So, and some of the things that one work I wanted to point it out is that, so there is, right, so what do we do? So, right, are you actually realizing some of this? So there is a company called NMS Works, that is actually building analytics and machine learning framework for 5G networks, which I am helping the team, right? So this is essentially a system that continuously collects data, right, related to network and system events, and then uses the machine learning systems to provide insights on network behavior and so on. So there are a couple of use cases that this system actually has been tried out with. And this is again part of the 5G testbed that we are currently building at IIT Madras. Okay, so this is overall system, right, composition or components, very similar to what we saw before. There are various network functions, and there is a system that monitors the overall utilization of the system and the various parameters and metrics, and then decides what action to take in particular. Okay, so for instance, the one of the use case was to identify anomalous behavior in a UPF. Okay, so UPF is again a user plane function which is part of the 5G core, and we keep tracking various performance indicators. These are what the metrics, right? So amount of data coming in on GTP data packets, and what is the data packet loss, and what is the average uplink packet delay, and what is the link utilization. So these data we monitor, then we try to come up with a machine learning model that tells us whether there's anomaly or not. Okay, so again, the machine learning technique used was multivariate Gaussian distribution. So this data was collected over a period of time and then fed it to this distribution, and then based on that we predict whether we are able to achieve detection of anomalous behavior or not. Okay, so this, for example, graph shows you these are the 4 metrics, right, that we saw, and this is again varying with time, right? You can see this axis are moving along with time, and wherever these little x's that you see, the red color X mark, okay, these indicate that this is where anomaly is observed, right? So in this graph, you can see that there is some spike here. That's an anomaly. Whereas here, there is no such spike, but it's still, right, looking at the data volume, it is packet loss is high here, but data volume is low here, which means that something has happened. That's why the data volume is low, and therefore this same X mark here indicates that these are anomalous behaviors. And we look at delay as well as link utilization. So when link utilization goes very low, and it again, these 4 parameters define what is anomaly. It's not just one parameter, right? I would look at multiple parameters and build a model that says when a combination of these parametrics show that something is wrong, then my system is anomalous behavior, right? And then you want to take any corrective action based on that. So that's what this NMS frameworks is trying to do. Okay. So with that, we pretty much are at the end. And my lab, we are doing a set of related problems. I won't delve much into this. If people are interested, they can contact me. We are looking at how to do load balancing in network slice allocation and virtual network embedding. These are all still works in progress. We have no publications yet, but we are trying to look at network embedding. Again, resource allocation problems in 5G network is what we're trying to do. Okay, and slice admission control. So these are all kind of too detailed now to explain. So I will skip it. I just wanted to finish with an indication of what we are trying to do in our lab at IIT Madras. Okay. So with that, I will stop. Thank you for your time. It's 2 hours. Questions?
Sir, there's one question which is posted in the chat box, sir.
Okay, let me check. How is applied to healthcare applications? Okay, very good question. Like I said, I do not, I've seen RL in the context of networking systems only. I have not seen RL to healthcare, but the basic premise is this. See, you should understand what a technique is trying to do. See, reinforcement learning, right? It's like how do you teach a child to walk, right? The child tries to walk, it falls down, right? And it gets up. Now there is a lot of neural network processing that goes on that tells the child, right, how to balance itself, right? So that is, again, we are not actually guiding the child in any particular way. It learns, it falls, it learns, it falls, it learns, and so on, right? So some sort of knowledge base is built where it knows, okay, at some point in time, right, I should sit down rather than fall. And in the context of healthcare application, you should try to see what is the application I'm trying to build, right? And what is the natural technique to use for this particular application, right? You saw that list I had given for networking, right? There are various use cases, right? Operation management, resource planning, security, right? Assurance, fault tolerance, and so on. And for each of those, right, there's probably 1 or 2 techniques that are most suitable. And that requires understanding of the domain knowledge. Okay. So what happens is people sometimes blindly apply, I know technique A, B, and C, let me apply that to this problem. Okay. that will not give you sort of a good feeling, right? Or any concrete or meaningful result. So it really depends upon what am I trying to do, right? So if you look at RL, right, robotics is a common thing that people have used RL a lot in, because how do you teach a robot to move around, right? You have it basically tries to move, it hits an obstacle, then it remembers that, right? The reward is where it comes in. You feel, you know what, I hit an obstacle, I have to change my path. That is the sort of negative reward. That's how our systems try to learn. In healthcare, again, if you are looking at, say, for example, rehabilitation of elderly patients or stroke patients, etc., right? For those kind of scenarios, this may be very useful, because you have to give them feedback, right? For example, a stroke patient is trying to move the arms, right, kind of, or remove the fingers with some particular right exercise. And if there is an automatic way of getting input, motor input back to this RL device, that can then tell the patient how to move the arm later on. Okay, so this, like I said, really requires deep understanding what the domain is and what problem you're trying to solve. Okay, other questions?
Yes, sir. Any other questions? Participants, you can post it either in the chat box or you can unmute yourself and ask.
Okay, so then that's all right. If there are no questions, it's a long 2-hour session.
Thank you,
If
sir.
you have anything else, you can try to email me and I'll try to answer to the best extent possible. Okay,
Thank you
you
so
very
much,
much.
sir. Thank you for
It's a
your
pleasure.
valuable session, sir. Thank you for sharing your knowledge and valuable input, sir. I hope all the participants would have gained valuable insights on the topic of this session. Thank you all for attending and participating in this session actively. Thank you, sir.
Thank you very much. Good afternoon to all.
Thank you.
Bye.